How can FFT be efficient in real-time embedded systems? Imagine trying to listen to a song and analyze its different parts instantly. That's what real-time signal processing demands. When it comes to analyzing signals quickly and accurately, fast Fourier transform is a key tool. But in embedded systems, where resources are limited, making FFT efficient is a real challenge. So, how do engineers do it? Let's break it down. First, understanding what FFT does is important. It transforms a signal from the time domain into the frequency domain. This helps identify different frequencies in a signal. The basic algorithm for FFT reduces the number of calculations needed from a very high number to a much smaller one, making it faster. Instead of doing many calculations, it cleverly reorganizes the work to save time. One way to make FFT more efficient is to minimize how often you run it. Instead of performing an FFT after every tiny change, do it once after processing a batch of data. This saves processing power and speeds things up. Also, many embedded systems don't have floating point units, which are hardware parts that handle decimal calculations quickly. Using fixed-point arithmetic instead reduces the load on the processor and cuts power use, which is perfect for small devices. Another trick is to focus only on the important parts of the signal. Techniques like selective scaling help ignore insignificant frequencies, saving energy and processing time. Hardware-specific features also play a big role. Many microcontrollers and digital signal processors have dedicated hardware modules for FFT. These modules perform calculations faster and with less power than software alone. Modern embedded processors often support vector processing or single instruction multiple data instructions. These allow multiple calculations at once, speeding up the FFT process. To make the most of this, data should be stored in fast memory close to the processor, reducing delays caused by slow memory. Using optimized software libraries designed for embedded systems is another key. Libraries like CMSIS Digital Signal Processing for ARM Cortex processors are tuned to run efficiently on specific hardware. Pre-computing parts of the FFT, like twiddle factors, before runtime also helps reduce delays during actual processing. Power management is essential. Efficient FFT implementations cut down on unnecessary calculations, which lowers energy use. Sometimes, using multiple cores or even graphics processing units can boost speed, but this must be balanced with power limits. In electrical engineering, these optimized FFT techniques are used in many real-time applications. For example, in motor control, power quality monitoring, or communication systems, quick frequency analysis is vital. In embedded deep learning, FFT-based methods speed up neural network tasks by transforming data into the frequency domain, making real-time processing possible on small devices. In summary, making FFT efficient in embedded systems involves smart algorithms that cut down calculations, hardware features that accelerate processing, and software that's tailored for limited resources. Combining these strategies helps ensure that FFT can deliver fast, accurate results within the tight constraints of real-time embedded applications.